Learning statistics and navigating life, for that matter, is done more effectively as one looks at the big ideas and avoids getting lost in the minutiae of the details. Running a z-test of one proportion is so much like running a z-test for a mean. We're going to test the dice rolled in the shady underground casino to determine if a 1 is rolled more than 1/6 of the time. A random sample of 60 rolls of the dice was taken. A 1 was rolled 16 times. Step 1 of our write-up. The parameter is the unknown proportion of times a 1 is rolled on these dice, not on a fair die. We already know the true proportion of a fair die. Here's the claim, the complement, and due to the complement containing the statement that the unknown proportion could equal that of a fair die, it becomes the null hypothesis. We're running a z-test on our parameter. We trust the approximate normality of our sampling distribution displaying how sample proportions from a fair die would behave. It displays solid understanding to the AP reader to state the expected number of successes and failures are both at least 10. We were told that a random sample of 60 rolls of the dice was taken. This ensures random behavior of dice and thus the sample proportions, otherwise the sampling distribution would not be an accurate representation. Allowing bias in what rolls got recorded could produce a biased sample proportion as an estimator. We can trust the standard deviation formula since the population is at least 10 times greater than the sample of size 60, because in the case of the underground casino that you never should have gone to in the first place, the dice are used many times. The test statistic is still the difference between the statistic and the parameter in terms of the number of standard deviations apart. If the difference is large enough that we no longer believe it's due to random chance, we'll consider it a statistically significant difference and reject the null. We should show the tail on which we're calculating the probability so that the reader recognizes our understanding of calculating the correct p-value in terms of the specific alternative hypothesis. It's wise to continue using the script for the conclusion. Because the probability of a type 1 error is less than 0.05, we reject the null. The evidence suggests that the proportion of ones rolled exceeds that of a fair die, supporting the concern voiced in the situation that more than 1/6 of the rolls are going to be a 1. Remember that the p-value is the probability of a type 1 error, because we assume the die was fair through the process of calculating the likeliness of getting a result at least as extreme as our sample proportion due to random chance if the die was fair. Also, because our test statistic is the z-score from a sample result using a normal distribution to approximate, we can still compare it to the critical z-score that traps 5% of the right tail to determine if our sample result was extreme enough to reject the null at the 5% level of significance. In games using dice, it can be bad if a die is not fair in either direction. So if someone had simply claimed the proportion of ones is not 1/6, then this would become a two-tailed test. We would calculate the same test statistic, but it would be very important to display our understanding that our p-value is the probability of an extreme result due to chance occurring on either tail. This would double the probability of 0.0188 from just the right tail. This makes sense if you remember that when we calculate this, we're still assuming the null is true and that the die is fair, assuming the extreme result is just due to random chance tempting us to reject the null, and if it's all just happening due to chance anyway, it could just as likely been that our sample proportion was equally extreme below the proportion of ones rolled on a fair die. And the graphing calculator will compute the correct p-value based upon what you enter as the alternative hypothesis. No need for you to double the p-value. That's shown in the next video.